Hello AP Statistics students. In this video, we're going to start taking a look at tree diagrams. It's another way to organize the information about probability for a scenario. Now, why do we need another way to organize probabilities? Well, this one's nice because the tree diagram has a lot of the possible conditional probabilities already in it. And once you have those, it's actually very easy to calculate your joint probabilities, the ands. So I want to make sure you see these and you know how to use a tree diagram. So first example here. Because I'm super original and I have many great ideas, we're going to go back to our gender versus ear piercing data set and convert it into a tree diagram. So there's our raw data there about this sample of people. I think it was from a college or something. And they had both male and females participate and then asked them, hey, do you have a pierced ear or not? So there's our data. But instead of putting it in a two-way table, we are going to convert it into a tree diagram like this. So first thing you do is you take your data and you break it up with your first variable. Now you can choose which one you want to use first. In this case, we're going to do gender first. So male and female. And then you look at the probability for each of these to happen. Now, these are in the margins. So what is the probability that we pick a random person from this data and get a male? Well, that would be 90 out of 178. So we will do 90 divided by 178, and we will get 50.5. So usually you put it right here, 0.505. You'll put the probability along the branch of the tree there. And then the complement of that would have to be for female, right? You just do 1 minus that number, or you can do 88 divided by 178. Just do the other margin, and you get 0.494. There we go. All right, so now we've broken up by the first variable. Now it's time for the second variable. So now we're going to take all the males and break them up into those who have a piercing and those who do not. And we'll do the same thing for the females. Piercing and no piercing. But now we have to calculate these probabilities. A little tedious. So of the males, how many have a piercing and how many do not? Hopefully you can see that this is a conditional probability here. So for the yes, it is 19 out of 90 this time. So that is 0.21. And the rest here you can get easily because that's minus 100. That will be 0.79 roughly. Those two have to add up to 100. And now the females, 84 out of 88. Is 0.95. And then I'm just going to round here for the sake of simplicity and call this one 0.05. All right, there is our tree diagram, all done. Now again, what's the usefulness of this? Well, first, conditional probabilities are extremely easy. What is the probability that somebody has a piercing given they are male? Well, that means I'm only looking at the males. Which ones have a piercing? This 21%. We have our conditionals right in the tree diagram. So 21% of males have a piercing, ear piercing, or the probability of picking a random male that has a piercing is 21%. That's your given, that is your conditional. So all of these here are the conditional probabilities given a certain gender. Now, we're missing the other half, the other way you could ask that question. What is the probability of being male given you have a piercing? We'll get there. We'll get there. All right, the other really cool thing about the tree diagram are the joint probabilities. What is the probability of being female and having no piercing? The joints. Well, the joint is really easy to see on a two-way table, right? But where is it here? Well, there's a pretty fancy thing you can do. All you do is multiply down the tree diagram along the branch that has both of these. So the probability of being female is this, and no piercing is this one. So what we do is we multiply those two probabilities, 0.494 times 0.05 is equal to. So the probability of picking a random person that is both female and has no piercing is 2.5% roughly. Round that up a little bit. And hopefully that kind of makes sense there. Wow, it just did that math for me. That's kind of crazy, isn't it? 5% of the females have a piercing. Well, how many females were there? 49% of our sample. So 5% of means multiply, 5% of that 0.494 are females and have no ear piercing. Now, how's another way we can explain that? Well, it's with this general multiplication rule. All right. So here's a rule that the formula we used on Friday. The probability of A given B is equal to the probability of A and B divided by the probability of B. That's our conditional probability. Well, if we want to turn that into a multiplication rule for joint probabilities, all we do is multiply that denominator over, and we get a formula for the probability of A and B. So we're just solving for another part of the equation. So that will be the probability of A given B times the probability of B. Now, because the A and B part on the left, the order doesn't really matter. The probability of A and B is the same thing as the probability of B and A. We can actually switch these a little bit, and you can do this one both directions, is equal to the probability of B given A times, now here the denominator has to match with this, so that's the probability of A. So those are both the same. They will both give you the probability of A and B, just depending on what you're given and what your probability is. But that takes our conditional probability and turns it into what's called the general multiplication rule, which is these two things here. All right, let's do an example here. Hopefully that will sort of click a little bit. So, a certain AP Stat student, who shall remain nameless, has trouble getting up in the morning. The following tree diagram describes the probability this student will get to school on time depending on whether or not they hit the snooze button on their phone alarm. We've all been there. You were probably there this morning. All right, so was I. Here is our tree diagram. So there's a 60% chance this kid hits the snooze button, and there's a 40% chance they don't hit the snooze button, which I assume they then wake up. But that doesn't mean they get to school on time. So if they don't hit the snooze button and they get up, there's still only a 90% chance they get to school on time, and there's still a 10% chance that they will be late. Now, obviously, that's different if they hit the snooze button, am I right? So if they hit the snooze button, there's only a 70% chance they'll be on time and a 30% chance that they will be late. So, letter A, one of the probabilities on the tree diagram is 0.90. Interpret this probability in context. All right, so where is our 90? Right here. So that is the probability that they will be on time given they don't hit the snooze button. So this is the probability that the student gets to school on time given they did not hit the snooze button on their alarm. All right, there's a 90% chance they get to school given they don't hit the snooze button. That's the first thing you got to be able to do is interpret the numbers on the tree diagram. All right, what is the probability this student hits the snooze button and still gets to school on time? So it's a random day. All right, we don't know what's going to happen. What are the chances they hit the snooze button and still get to school on time? Well, that's a joint probability. So we're allowed to just multiply down the branches of the tree diagram. All right, so what do we want here? They hit the snooze button and still get to school on time. So they hit the snooze button, but they still get to school on time. So 70% of 60%. All right, we get to multiply those two. So 70% times 60%. So 42% of the time, or there is a 42% chance that on a random day, this student will hit the snooze button and still get to school on time. All right, those are pretty easy, aren't they? That's one reason why the tree diagram is pretty nice. Conditionals are right there for you, and joint probabilities are pretty darn easy. All right, time for some challenges. What is the probability that this student will get to school on time? Oh, so we're taking out the snooze button. Just what are the chances this student gets to school on time? This, if we had a two-way table, this would be in the margins. All right, we would just add up a row and divide by the total. But we don't have the margins. So we have to think, all right, what are the two ways this kid can get to school on time? Well, this would be the probability of them hitting the snooze and getting to school on time, plus the probability of not hitting the snooze and getting to school on time. Those are the only two ways this kid can get to school on time. They could hit the snooze button and get on time, or they could hit the snooze button or not hit the snooze button and get to school on time. And I am allowed to add those two probabilities because they are mutually exclusive. These two events cannot happen at the same time. The event as a whole, All right, hitting the snooze button and getting to school on time cannot happen at the same time as not hitting the snooze button and being on time. We get to add those. So we know one of those, right? Letter B was one of them. There's a 42% chance that they will hit the snooze button. So this one is 0.42 plus, I just need the second one. What are the chances of not hitting a snooze button and still getting to school on time? That is a joint probability. So that would be this one and that one, right? So 0.4 times 0.90. 0.4 times 0.9. 36%. So that is 78%. All right, so on a random day, there is a 78% chance this student gets to school on time. And there's two ways that could happen, but overall there's a 78% chance. All right, now the super challenge. This one is where the tree diagram is a little bit harder, but it's still possible. So what is the probability that this student hit the snooze button given they got to school late? All right, what is the probability this student hit the snooze button given they were late? Now, conditionals should be easy with a tree diagram. The problem is this is a different conditional. This is given that they were late. Our tree diagram is set up to be given they hit the snooze button. Oh, so now we got to go backwards somehow. How do we do that? Well, I think the easiest way is to go back to the formula. All right? The formula says that a given probability is the probability of both of them, so snooze and late, divided by the probability of being late. All right, so what will that be? Oops, keep me in the equation. There we go. All right, well, the top one is easy, right? Because snooze and late, we can just multiply on our tree diagram. So what is snooze and late? Snooze and late is 0.6 times 0.30. All right, not that it's going to help for me to draw another snake on here, but that one, right? There is snooze and late. So 0.6 times 0.30. 0.6 times 0.30 divided by the probability of being late. All right, now this is just like challenge number 1, only but for the late. And actually, it should just be the complement, right? If there's a 78% chance that they were on time, there better be a 22% chance that they're late, right? Those have to add up to 100. But let's pretend we don't know that. So how can they get to school late? Well, they could hit the snooze and be late. That is 0.6 times 0.30. What's the other way they can be late? They can not hit the snooze and be late. So what is that possibility? They could not hit the snooze and be late. That's this bottom one. So 0.4 times 0.10. 0.4 times 0.10. All right, then whatever the heck that fraction adds up to be. So be careful with the denominator. Make sure your order of operations don't mess you up. You can't just type that whole thing into a calculator unless your calculator can actually do fractions, which you may or may not be lucky enough to have. I don't remember what the 84 does. 0.6 times 0.30. Will this one turn this into a fraction for me? Nope. So if my calculator is not turning this into a fraction, so I got to be careful. The denominator has to be in parentheses. Plus 0.4 times 0.10. There we go. So see, my denominator is in parentheses. That way I know it will do the denominator first, then it will divide. So there is an 81% chance that this person hit the snooze if they walked into my class late. I'm looking at you. Just kidding. I'm not going to say your name. 0.81. So if you walk in late, I know there's an 81% chance you hit the snooze. All right. I want you to keep going in this here OneNote. I got 2 examples for you to try. Here's one. I started the tree diagram for you, and here's one where I did not. Try those out. Fill it out in the OneNote, please. Good luck.